Hello everyone, and welcome to the lecture on amortization. So we've already discussed dynamic arrays, we've implemented a dynamic array, and we've learned that when dynamic arrays get full, they double in size. So in this lecture, we're going to do an amortized analysis of dynamic arrays. So the strategy of replacing an array with a new, larger array might at first seem slow, since a single append operation may require order n time to perform. Our new array allows us to add n new elements before the array must be replaced again. So, what we're going to do is use an algorithmic design pattern called amortization. We can show that performing a sequence of such append operations on a dynamic array is actually quite efficient. So, again, just to reiterate, remember, if we have a current number of elements and we're going to overflow, that is, fill up the array, we're going to double it to get more room. But on that doubling, that means that primitive operations for an append is going to be order n. So here we have 1, on 2 we have to double, on 4 we're going to put a append, so it's going to be order n. On 8, again an append will be order 8. On 16, order 16. Everything else is just going to be order 1, or constant. So again, what we're going to do is allocate memory for a larger array of size, typically twice the old array. Copy the contents of the old array to the new array, and then free the old array. Let's go ahead and see a diagram of this process. So, here we have a dynamic array. Initially, we'll call it the table, it's just empty and the size is 0. Insert item 1, we're having an overflow since our array is full, so we have to double it. When we insert item 2, again we're having an overflow, the array is full, so we have to double it. On inserting item 3, you're fine, but inserting item 4, you have to double it because you're having an overflow. Then on 5, 6, and 7, you're alright. So let's do an analysis on this process. Here on the left, we have that same figure showing the insertions. And here on the right, we're actually going to do analysis. So for item number 1, for instance, our table size is 1. So our cost of putting that append or inserting it into that table or array is just 1. Item number 2, table size was 2, so our cost was 2, order n. And here's where basically the magic of the amortized analysis happens. On item number 3, the table size has become 4 since we doubled it, meaning our cost is 3. And then on item number 4, since we've already doubled the table size to 4, our cost is now just 1 for that insertion. Then on item 5 and table size 8, our cost is 5. But for 6, 7, and 8, since the table size is 8, our cost of insertion is actually just 1. So the amortized cost, we can actually sum this all up and divide it by n, the number of items in that array. And we can actually simplify that above series by breaking the terms 2, 3, 5, 9 into 2 as 1 plus 1, 1 plus 2, 1 plus 4, 1 plus 8. So we have those n terms, that 1 plus 1 plus 1, and then using a bit of a math trick, we can have the other ones go 1 plus 2 plus 4, etc., divided by n. Meaning we have n plus 2n over n, and when you divide n out, that will be just 1 plus 2, which is 3. So the amortized cost is actually constant at order 1. So, go ahead and check out the resource section of the lecture for a PDF of a more detailed explanation. That's going to be your homework assignment, so make sure you read that full PDF explanation. It's just a few pages long, but again, it's a nice amortized analysis. This isn't really necessary for you to know, given what the array interview questions are going to look like, but you should know it if you're interested in how a dynamic array works. So, up next, we're going to have a lecture overviewing the interview problems in this section of the course, and after that, we'll get started with the interview problems. Thanks everyone, and I'll see you at the next lecture.